This is the fourth part in our series of pathfinding. Previously, in the first episode, we looked into the graph representation of the level layout. We considered working but rather simple solution, so we will now take on this topic and proceed to more advanced and industry standard solution such as NavMesh, and we will also have a look at some graph smoothing techniques. In the third episode, I explained the operation of one of the most influential pathfinding algorithms, the Dijkstra algorithm. On this basis, I will now introduce a state-of-the-art A-star algorithm and its heuristics. If you haven't watched the previous parts, you should definitely do so, because this installment is just a small addition built upon the topics discussed in the previous parts of this series. So, the approach I introduced in the first episode is called points of visibility graph. This is because each pair of nodes with a connection has to satisfy the visibility condition. This creates quite a coarse but effective and first of all easy to create even manually representation of your level, but it has some weaknesses. You probably noticed that the path created by this algorithm is far from ideal. So we say it tends to create suboptimal paths. Also, it is very likely that due to a human error, if the points of visibility graph is created, of course, by a programmer manually, you can make some inaccessible or invisible map positions. Here on this diagram, they are marked with these exclamation marks. There is no visual connection between these corners here and any of the nodes of the graph. Sometimes it's very tricky to locate, to find, particularly if your layout is pretty much complicated. Therefore, a reasonably easy solution, the entire walkable area, so wherever you can walk within your map, can be divided into a network of convex polygons. Okay, it's the idea behind it is that it's much easier to define such polygons than to think about all those nodes and so on. And with this structure, which is the first step towards the technology known as NavMesh, and those of you who have some experience in Unity, you will recognize that this is a method of pathfinding applied in this game engine. So once we have defined these convex polygons, we can create for example, with finely grained graphs. They provide a better, smoother paths and better accessibility. But first of all, they guarantee that each location will be reasonably well accessible from this graph. And also they are quite easy to be generated programmatically. And how? Quite easily. This is a simple flood fill algorithm. So in this algorithm, we start from a single point, single node somewhere. And then let's just imagine that we have a square grid over this level. So with this square grid, we can just analyze all the potential possible neighbors. 1, 2, 3, 4, 5, 6, 7, 8. There will be eight neighbors around. And of course, for each neighbor, we check the visibility. We do the visibility test. And in this case, we can start with two neighbors, perhaps even more neighbors, okay? We won't take any nodes that do not satisfy the visibility test. And basically, the simple flat fill algorithm will, after creating these two initial conditions, will iterate through all undone nodes, so all new nodes, and will repeat the same procedure, finding the neighbors of neighbors, the neighbors of neighbors of neighbors, neighbors of neighbors of neighbors of neighbors, and so on, so on, so on, until the entire available space is filled with the graph. So it's reasonably easy to program. But still, even with this finely grained graph, the path created will be not exactly optimal, because the character will still have to move on from one node to another node, and eventually you can get, for example, a path line like this, okay, with some completely unnecessary turns on the way. And this is when the path smoothing algorithm comes very, very handy. How you can do it? This is reasonably simple, another reasonably simple algorithm, which always look into 3 consecutive points. So, for example, points A, B, and C. And now, if there is a unobstructed, so visible pathway between A and C, then we can remove the B from the path and provide a direct connection from A to C. This is, please note that there doesn't have to be a connection like this in the graph, okay? So the structure of the graph is like here, and AC is a kind of a shortcut between two nodes of the graph that otherwise are not connected. And of course, if there is an obstacle on the way, we do nothing. So if you have an obstacle like this, we will remain with A, B, C structure. So let's have a look at some example. We will move on from S to T through a path that consists of nodes 1, 2, 3, 4, 5. And you can notice that this path is not very optimal, but in every step of this algorithm should be iteratively repeated from farther and farther segments of this path. In each iteration, we look into 3 consecutive nodes, so 2 edges, okay? 2 edges, edge number 1 and edge number 2. And of course, there is a visible connection from the start node or 0 node to node 2. So we will exclude 1 from the path and create a direct route from S to 2. Please note that this breaks the structure of our graph, but it doesn't matter that when the character follows the edges of the graph. It's better like this because the character follows more straight route. Okay, so we now again look into E1, E2, but this time is E1 is from S to 2, E2 is from 2 to 3, and again there is a visible route from S to 3. And please note we started with a very coarse route, and now there is a straight line from S to 3. Now we cannot optimize this situation because there is an obstacle between S and 4, so we leave this situation as it was, and a similar situation with 3, 4, 5. There is no possible way between these nodes, but there is a possibility to find a shortcut bypassing node number 5, so directly from 4 to T, and without further details, the final path looks like this, much better than the original. Moving on to the algorithms. Let's revisit the Dijkstra algorithm and find out some of its most serious weaknesses. Here is the example we used in the previous episode of this lecture. We're finding the path from the start, node number 3, to the goal, node number 8. The red line shows the path that was found, but we can see here all the nodes that have been visited at least once during the algorithm execution. And with a dark blue color, there are the closed nodes shown. And you can see that for an algorithm looking for this kind of a path from 3 to 8, visiting one is quite reasonable. 0, let's say, but 17, 16, it's a totally different direction. Here is a more complex example. So this was the Dijkstra algorithm running to find a path from a start which was here to a goal which was here. And you can see consecutive stages of this algorithm with black nodes symbolizing closed nodes, and those gray nodes, these are open nodes. By the time the algorithm finished by finding the path, and this path is nicely this way here, okay, but the closed nodes are all over the graph, and open nodes are also everywhere. There is actually a very small number of unvisited nodes. So the question is, can we possibly improve it? And you guess, yes, well, of course we can. Dijkstra searches entire graph indiscriminately. It's not a bad thing as you might think, because the algorithm was originally designed, just a reminder, in the 50s of the 20th century, like 70 years ago. And this algorithm was designed to find the shortest path to every possible node. So it had to flood the entire graph. It wasn't anything wrong about it. But for our purpose, for gaming application, when we just want to find a single path to a single node, anyway, we depart from the purist algorithm because we stop iterations once the goal node is taken. So it's already some step forward from the original Dijkstra. But can we do it better? Of course we can. So-called A-star algorithm is specifically designed for point-to-point pathfinding. It's very similar to Dijkstra. It's nearly identical, but it's just one major difference. Dijkstra selects the current node from the open list as the node with the minimum cost so far. And A-star goes one step further. It selects the current node as the minimum total path length from the open list. But how is that possible? How this algorithm could possibly know the total path length from the start to the goal node? Well, it doesn't. It just makes a guess. Alright, so A-star estimates the total length of the path. This is the length going through a particular node as sum of the costs so far, so the value that is known and calculated in the Dijkstra algorithm already, plus the heuristic path to goal. Heuristics is a practical method of estimation that is not guaranteed to be optimal or to be precise. It may be just sufficient. So this is a kind of an educated guess. So A-star needs to guess what's the remaining distance after the cost so far, what's the remaining distance from the current position all the way to the goal node. Here are some examples of heuristics. The easiest one and actually the most often used is just the Euclidean distance. So you measure the distance from the node to the goal as the crow flies. And this means that nodes closer to the goal in terms of Euclidean distance, the closer nodes will be selected earlier in the process. And this can change a lot. Another example of more sophisticated heuristics, so-called cluster heuristics. Nodes can be divided into clusters or regions with a kind of a lookup table to quickly find the distance between those regions. And in this way, the nodes likely to be closer to the goal are selected. And there is also quite a funny thing, zero heuristics. Zero heuristics is the heuristics that always return zero. It sounds funny, it just tells, oh, for every node, the remaining path to the goal is just zero. But if you apply the zero heuristics, your A star becomes identical to Dijkstra, because the total length from this formula that we've seen a moment ago is just cost so far plus zero. So it's exactly what the Dijkstra does. Actually, Dijkstra is the A star algorithm with the zero heuristics. Okay, there's one more difference between A star and Dijkstra. Unlike Dijkstra, in A star, there is no guarantee that closed nodes could not be improved. A better path can be found to a closed node. In such a case, the node and the connection must be updated, and the node requires reopening, so once a closed node can go back to the open list. If you were implementing Dijkstra algorithm following my pseudocode, you might have noticed that this pseudocode does not take this improvement, perhaps, that closed nodes are guaranteed to be optimal. Actually, every node is meticulously checked whether the new cost so far is better than the old cost so far, and the pseudocode doesn't exclude the closed nodes. This is simply because I created a pseudocode that is, well, A star ready in a way. Okay, so you when you change Dijkstra to A star, you don't have to do this simple detail, but still, if it happens that the closed node is you have discovered a better route to this closed node, you have to reopen it, so bring it back to the open list. Okay, A star may produce suboptimal paths, and in many cases it will, but quite often the path found by A star will actually be optimal. Its performance, well, I will tell it briefly, is sufficient for the algorithm to be absolutely dominating #1 pathfinding algorithm in the games production and games industry. A star is a dramatic improvement over Dijkstra. Kevin Wong published on YouTube a comparison between both algorithms. This is one of the races in which Dijkstra is not only slower but practically floods the entire area, whilst A star is faster and straight to the point. You will find the link to this video somewhere here. This is the final installment of the Pathfinding series of AI lectures, and at least as for 2020, also the last lecture on AI. So I thank you very much for watching, not only this, but all previous lectures, and I invite you to watch my 3D lectures.